Welcome to that of the UG and PG students. Now we are going to that of the next question solution 2024 for the second part. In the second part, we are go to that of the first question regarding the dissociation of the gem diol. Here the gem diol can be dissociated to form the carbonyl compound. Here the three type of compounds are given P, Q and R. In the chloral compound can be stabilized in the gem diol form via intramolecular hydrogen bonding, so it cannot be dissociated to that of the carbonyl compound. But the acetophenone has the highest steric interaction, so it readily eliminates the water molecule to give that of the carbonyl compound. Hence, the dissociation constant order for that of the R compound is greater compared to that of the P compared to that of the Q. Here the Q is the last because it is stable in the hydrogen bonding form. Here the some compound are given where the compound mainly is not stable in the hemiacetal form. Here this compound is stabilized in the hemiacetal form. By the equilibrium go to that of the forward direction, cyclic hemiacetal form is stabilized. Here the cyclic form can stabilizes this hemiacetal form. Next, the conformation of cycloalkane, cyclohexane. Cyclohexane can be stabilized in the here the carbonyl group and the hydroxy group is present. Here the carbonyl and the hydroxyl group can be stabilized via intermolecular hydrogen bonding effect or intramolecular hydrogen bonding effect. Here the hydroxyl group can stabilize via intramolecular hydrogen bonding effect in isooctane, that is the non-polar medium. And so the option B will predominate in isooctane due to intramolecular hydrogen bonding effect. Again, the intermolecular hydrogen bonding effect occurs in that of the DMSO, but it is not stable in the equatorial form, as the steric interaction will occur with that of the large substitution of the axial group, and hence it is stable in this A form where the dipolar interaction is minimized. So the option A predominate in DMSO due to opposite dipole interaction, and the 4 option B predominates in isooctane due to intramolecular hydrogen bonding effect. Here the lone pair interaction unstabilizes the equatorial form in the DMSO medium, and in the lone pair interaction is minimized when the hydroxyl group present in the axial orientation. This is the problem from the mass fragmentation. You know that the mass fragmentation for that of the benzylic system readily cleave the hydrogen atom, hydrogen radicals, and form the tropylium cation. And here the benzylic alcohol derivatives P compound can be cleaved by Mackler-Fertig type reagent by the elimination of the water molecule and produces the more stable compound diene derivatives, and the M/Z ratio, that is the mass of this compound, becomes 104. But corresponding the phenol derivatives, 2-ethyl phenol, where the cleavage occurs by the methyl radicals, and to give that of the M/Z ratio 107. This radical mechanism occurs via the elimination of the alkyl groups. This is the examples of the chemoselective oxidation. We know that the chemoselective oxidation means the similar type of the functional group is present in these molecules, but particularly we can oxidize one functional group in the presence of other functional group. Here the para-toluene sulfonic acid in presence of the diacetyl derivative of acetone produces the cyclic acetal, where the cyclic acetal means the cis hydroxyl group, the cyclic acetal is formed, and to give that of the cyclic acetal derivatives, and these cyclic acetal derivatives on Dess-Martin para-iodide oxidation, here the 2 hydroxyl group is open, so that there is possibility to oxidize the 2 hydroxyl group, so the desired carbonyl product is not obtained, so the option 1 is wrong. In the second option, the tetryl chloride, triphenyl methyl chloride can protected only the primary alcohol in presence of the other alcohol, and then the dimethyl acetone derivatives to give that of the cyclic acetyl derivative in presence of the paratoluene sulfonic acid, and then oxidized by the Des-Martin pyridate oxidation selectively oxidize this hydroxyl group to give that of the carbonyl compound. So the option 2 is the correct. In the third option there is only the tetraethyl trimethyl silyl chloride, phenyl methyl chloride is protected only the primary alcohol group, and other hydroxyl remain intact, and this has possibility to give that of the carbonyl compound in presence of the Des-Martin pyridate. Here the no protection is present, so this option is also wrong. So the option 2 is correct. Similarly, this observation also taken from that of the Claydon group, where the carbohydrate molecules contain the different type of the hydroxyl group, where the triphenyl methyl chloride is used for the protection of the primary alcohol in presence of the other alcohol, and the cis hydroxyl group is used for the protection of the cyclic acetone derivatives, and using this technique we can selectively oxidize the free hydroxyl group in the presence of other hydroxyl group. This is the examples of the intermolecular Hague reaction, where the two alka-aryl group can be present in the trans orientation. Here the hydride palladium hydride elimination take place, followed by that of the another aryl group addition. At first, the phenyl group is present in the below sides, so the methyl iodide can approach to that of the opposite side to that of the phenyl group, and the beta hydrogen elimination occurs in that way. That is, after the addition of the aryl group, the beta hydrogen elimination occurs in the another carbon atom, where the hydrogen and palladium present in the cis orientation to give that of the alkene. So the phenyl and the naphthyl present in the opposite orientation, and the double bond present at the another position, and one option is the correct option. This is the examples of the elimination versus fragmentation reactions. Here the fragmentation reaction means the two eliminating group must be present in the anti-periplanar orientation. Here the lone pair and the chloride present in the anti-periplanar orientation, and the fragmentation will occur by the cleavage of the CC bond to produces the bi-member nitrogen containing heterocycles molecules, and hence the option A is the correct, means the 3 option. Again, in case of the compound B, case of compound product B, the only the anti-elimination, that is the stereoelectronic requirement for the anti-elimination is that the two leaving group must be present in the anti-periplanar orientation. Here the hydrogen and the chlorine present in the anti-periplanar orientation, so the elimination will occur and we get the compound B. So the first one is the examples of the fragmentation reaction, and the second one is the examples of the simple elimination reaction. And this is the examples taken from that of the Claydon groups, where the fragmentation reaction take place and then Robinson annihilation to give that compound. This is the examples of the some name reactions, where the Pitzer-Moffett oxidations in presence of the DCC, the alcohol molecule can be oxidized to give that of the carbonyl compound. Here the DCC oxidation can take place. At first the DMSO can attack to that of the dicyclohexyl imine to give that compound, and then after the elimination of the dicyclohexyl urea, it produces the reactive species which underwent elimination of the hydrogen molecules to give that of the carbonyl compound. The Swan oxidation can also take place in presence of the oxalyl chloride. Here the sulfonyl chloride is produced, and this is the active agent for the oxidation of the any alcohol by the similar mechanism, where the alcohol molecule can attack the sulfur atom to produces this sulfanium ion type species, and then the elimination of this hydrogen atom to give the carbonyl compound. Again, in the return reaction, the 3-degree alcohol can convert it to that of the tertiary butyl substituted primary amines, where the elimination can take place the water molecule and the nitrogen atom is attacked here by the hard center to produces the amide intermediate, and then hydrolysis of this amide intermediate to give that of the tertiary butyl substituted primary derivative. And in case of the Villers-Marek formulation, the intermediate is that the POCl3 first react with that of the N,N-dimethyl formamide DMF to produces the ionic species, and then this ionic species is react with the aromatic substituted derivative to give that of the formyl substituted derivative. So the option 4 is the correct, where the A is matches with that of the Swan oxidation intermediate, and the B is matches with that of the Villers-Marek formyl intermediate, and the C is matches with that of the Pfizer-Popper oxidation process, and the D is matches with that of the return reaction. This is the examples for the use of the chiral auxiliary for the introduction of the chiral substituent in the cyclic moiety. Here this is the chiral auxiliary, and where the butyl group is present in the above direction, and if we use that of the Zimmermann-Traxel type model, from that model we can see that the cyclic 6-member tension state chair-like tension state, where the OH group after the addition of the coordinated with that of the boron triplet, it produces a intermediate, and then the two alkyl substituent present in the below direction means this alkyl substituent present in the below direction, and this hydroxyl group is also after the addition, this hydroxyl group is also present in the below direction. So this alkyl substituent and this hydroxyl group both are present in the below direction, and after that the olefin metathesis reaction produces the olefin carbene intermediate, and then the intramolecular reaction to give that of the cycloalkene intermediate, and the lithium borohydride is used for that of the reduction of the amide derivative to give that of the alcohol product. So the option 1 is the correct. In case of the halogenation of pyridine, here the halogenation of pyridine can take place in presence of the sulfur trioxide with that of the sulfuric acid. Sulfur trioxide can coordinate with that of the nitrogen lone pair to produces the ionic intermediate, and then this ionic intermediate has no lone pair to attack the bromine molecules. Here one problem is that if bromine molecule is added here, directly can capture the lone pair on the bromine atom, so the bromination is inhibited or stopped. To prevent that, the sulfur trioxide is used, where the sulfur trioxide capture the lone pair on the pyridine, and hence the bromine molecule can added here with respect to that of the 3 position on the nitrogen atom, and then after the elimination of the HBr we get the 3-bromopyridine derivatives. So the intermediate for the pyridination of the bromine in presence of the sulfur trioxide is the 2. Next is the example of the Poisson-Khand reaction. In the Poisson-Khand reaction, cobalt octacarbonyl is used, and dimeric form of this cobalt octacarbonyl is react with that of the, actually it release that of the carbon monoxide, and it can add with that of the carbon monoxide in that fashion to give that of the cyclopentanone intermediate. Here the option 4 is the match with that of the cyclopentanone intermediate after the carbon monoxide addition. So the option 4 is the correct. This is the examples of the Beer-Villiger oxidation, where in the Beer-Villiger oxidation, alkyl group is migrated to that of the oxygen atom after the nucleophilic addition to that of the carbonyl group, and we get the ester molecule, and this cyclic ester after cleavage to gives that of the alcohol and the carboxyl group, and this carboxyl group has greater probability for the elimination of the water molecule to give that of the lactone derivatives, and this electron derivative contain the hydrogen atom in the upsides. So the substituent in the present in that of the downside, and since downside is more sterically hindered, so the alkyl group after the elimination of the hydrogen atom in presence of the LDA, alkyl group must come to that of the above side, and hence the above alkyl group is in the go to that of the top side to give that of the desired product. So the option 1 is the correct, that is the Beer-Blazer oxidation, followed by that of the elimination of the, after that the reduction of this diol to give that of the lactone to lactol. So the option 1 is correct, that is the Beer-Blazer oxidation, then the methylation in presence of the LDA, then diol reduction. Radical migration is the main key factor for the rearrangement reaction, but it is less favorable compared to that of the nucleophilic rearrangement. We know that the rearrangement, this is the 1 to 2 shift type reaction, and the W is migrated from the A center to that of the B center. During the migration, the 3-member cyclic intermediate is followed, and 3-member cyclic intermediate in the nucleophilic rearrangement, the lone pair, that is the electron, is present on that of the W atom, and it is migrated to that of the B atom. So the nucleophilic, that is the only one arrow is maintained, so only 2 electron is participate. So this is the aromatic type transition state according to first rule. We know that the first rule, this is the bonding electron is stabilized, so this is the aromatic. So nucleophilic rearrangement, that is the 1 to shift for nucleophilic rearrangement case, is more favorable compared to that of the periodical, where the single electron present in the antibonding orbital, so it is less favorable, and the electrophilic rearrangement 1 to shift is very less favorable, as the 2 unpaired electron present in the antibonding orbitals. The given problem is that of the radical rearrangement in presence of the 1 to shift in new pentyl derivatives, where the X can be alkene or the carbonyl pivotyl chloride, pivotyl carbonyl compound, or the cyanide. Here we know that the electron rich species is more migrated favorably compared to that of the electron deficient substituent. So here the electron rich migrating group is the alkene, and the electron deficient migrating group is the cyanide. So the electron rich species has greater migration aptitude. This is taken from that of the Jerry-Mart group. The migration aptitude is in the aura, that is the alkene, carbonyl, phenyl, and the tertiary butyl and the cyanide. So the order is that the P greater than Q greater than R. This is the problem from that of the sigmatropic rearrangement, where the alkyl group is migrated to that of the 1 carbon to 5 atoms. So that is the 1,5 alkyl shift. We know that the 1,5 alkyl shift is the retention configuration. So the retention configuration takes place. After that, the desired product can be obtained by the hydrogen migration with that of the 1,5 hydrogen shift to give that of the our given product. So the 1,5 alkyl shift and the 1,5 hydrogen shift with retention configuration is the option. So the option 4 is the correct. Thank you.